solve this problem together. We are going to implement this method using recursion. So we first need to define the base case, and that is going to be our first case. And that means if the given key matches the self key, then what we just need to do is update the new value. Okay, so that is the first case and our base case. And the second case is we need to find the right place to find this key. So if this key is smaller than the key stored in the current node, and then we need to have a look at the left part. We need to inspect the left part. And if the left part is none, that means we just need to create a new node with this key and value. And if left part is not none, then what we are going to do is call this insert method again for the left part. That's what we are going to do. So be careful. If this key is the same as the current key, then we just need to update the value of the current node. However, if this key is smaller than the current key of the current node, then we just need to inspect the left part. And if the left part is none, that means we reached the end. So we are going to just create a new node using this expression. Otherwise, we keep searching for the right place on the left part. So the last case is when key is larger than self's key. In this case, we are going to do a similar thing. We just need to check whether the right part is none or not. If it is none, we're going to create a new node with the given key and value like this. Otherwise, we're going to keep looking for the right place using the insert method like this. Do you have any questions regarding this method? Cool, let's move on. So up to this point, we defined binary search tree, and we had a look at how we can find a node in the given binary search tree. And using this, we developed this find method and implemented how we can find the smallest key or the largest key in the binary search tree. And we had a look at how we can insert a new key or update the key already inside the binary search tree using this insert method. And the next step we are going to take is implementing the remove method. So we had a look at how we can update a node or create a new node. And the next step is how we can delete an existing node. Deleting an existing node is quite tricky. So I'm going to explain how we can implement this remove method first. And then I'm going to show you how we can implement the concept. And we need to think about two cases. The first case is, of course, we just assume that this binary search tree has the key past this one. Okay, we are not going to check the error case here. So when we want to remove a key from this binary search tree, there's going to be two cases. The first case is the node of interest has 1 or 0 child. So let's say we want to remove 11. And this one has 0 child. And if that is the case, what we need to do is just remove the node. Or possibly we need to create a new connection or substitution. Substitution. So what I mean by this is, let's say we want to remove 11. And because this one has 0 child, we just need to remove this one. And that's all. However, if we want to remove 9, and this one has just 1 child, then what we can do is just remove this one and substitute this one with its child. So 7 will go here. Okay? So if the node we want to delete or remove has just 1 or 0 child, the things are very simple. Just remove that one and replace that one with its child. That's all we need to do. And the second case is somewhat tricky. The node of interest we want to remove has 2 children. In this case, things are somewhat complicated because we need to maintain the BST property. So what was BST property? The value in its node, in each node, must be greater than any value stored in left subtree, and the value in each node must be less than any values stored in its right subtree. So these two properties are BST properties. And when we remove, let's say 5, then this one has 2 children. And after removing this 5, we still need to maintain the binary search tree properties. So how can you do that? This one takes 2 steps. The first step is, of course, we need to remove the node. So what we are going to do is just remove this one. Okay, that's what we are going to do. And the second step, when we remove a node with 2 children, is exchange the deleted node with the smallest value in the right subtree. Okay, so what does it mean? The smallest value in the right subtree. So this one, originally 5, has a right subtree here, 9, 7, and 11. And what we are going to do is remove this one first and go to the right part and find the smallest value in its right subtree. So we are going to find the smallest value here, and that is going to be 7. Because when we want to find the smallest value, we just go to the end of the left part, and that is going to be 7. And we are going to remove this one like this and place 7 here. Then the BST properties are maintained. Why is it so? Because this value is the smallest value in the right subtree. However, because it was in the right part, it is larger than any values on the left part. So if we place that value to the root, then the binary search tree properties are going to be maintained. So that's why we are trying to find the smallest value in the right subtree and place that value at the root position as a new root. So this concept might be somewhat complicated or confusing at a first glance. However, this one is very simple when you once understand it. Any questions regarding this concept before we start implementing this method? All right, let's move on. So what we are going to do is check whether this given key is smaller than the key stored. And we need to check whether the left part is not none. Otherwise, we cannot repeating the searching process. And if we have the left part, then we're going to replace the left part with the remove key. And the thing is, this remove method is going to return the new node, new root. So why is it so? So let's say we want to remove 9. Then I told you that we need to replace this 9 with its only child, 11. So if this method returns 11 when we are trying to remove 9, then we can just place this 11 to this value. So that's why we are returning the new root. Once I finish implementing this method, this concept will be clear. So if we have the left part, then we go to the left part and call this remove method. And else if key is larger than self key and self right is not none, we do the same thing. Self right is going to be self right dot remove. And this is the case where key, the given key matches the key stored in the node. And we need to think about two cases. We need to think about the second case first. We have 2 children. What we are going to do is first check whether we have the left part or not. And self right is not none. So because left part is not none and the right part is not none, that means this node has 2 children. So this is the second case we discussed. Then we need to remove self, okay? And I told you that we need to find the smallest value in the right subtree. And what we are going to do is self right. We call this find first method on the right part, like this. And this one will return the smallest value in the right subtree. And we're going to replace the key with this one. So we found this node, which was 7 here. And we're replacing this value, the root value, with the 7 node. So this is what we are doing here. And we need to update the right part. And how are we going to do that? We're going to call a method called remove first here. Okay, and this will update this part. So this one, 7 goes here, and then so 7 still remains here. And we're going to delete this node. Then remove 5 is complete. All right. So this was our second case. And we need to think about the first case as well. That is, we're going to just return self left if self left is not none. Else, we are going to return self right. So we don't have this one because. So if we have left part, then we are going to just return the left one. Otherwise, we're going to return self right. And because when we remove this part, if we have the right child, then this one will return this node. And automatically, this will go to this position when we try to remove the node with the value 9. Okay? And lastly, we're going to return self. So this is how we can implement the remove method. And one more thing we need to do is implementing remove first. Okay? By the way, do you have any questions regarding this remove method? This one might look somewhat confusing at a first glance, as I told you. But you could think about it over and over, and I am pretty sure that you could understand this. Okay, and the next method we need to implement is remove first. This one, remove the node with the smallest key in the subtree rooted at this node, at the given node. And this one returns the new root as well. So this one is our PPP exercise. Try to implement this method